morning, everybody. It's my pleasure today to, to introduce Dr. Marco Simonetti. He is an associate professor of building physics and thermodynamics at Politecnico di Torino, with more than 20 years of experience as an academic and as HVAC project engineer and construction supervisor. His research and teaching activities have been focused on innovative and sustainable design of buildings through the study of human comfort, the application of low exergy technologies, and the exploitation of renewable energy sources. Dr. Simonetti co-authored more than 50 publications in peer-reviewed journals and conferences, and co-invented 6 patents, 5 granted, and 1 is pending. He is the co-founder of 3 startups and academic spin-off companies, recently in the framework of a collaboration agreement between Politecnico di Torino and the WHO. Simonetti's team is studying, testing, and delivering innovative design of natural hybrid ventilation of building optimized for the control of air vector of COVID-19 and other airborne diseases in hospitals, tertiary, and residential buildings. He visits regularly and collaborates with colleagues at Andlinger Center of Energy and Environment at Princeton University in the USA. Welcome, Dr. Simonetti. Okay, the floor is yours.
Okay, good morning, everybody. Thank you so much for this presentation and for inviting me here. I'm very happy. It's my 3rd time here in Beirut, and I always come with a great pleasure. And I find high scientific level and very, very good friends and hosts. Okay, so for today, I'm going to talk a bit about recent experience and traumatic experience with COVID and its relation with our building service. I wanted just to make a disclaimer, so to say, like I am not just strictly an academic. I have been also designing HVAC system for some 15 years. So, So my position is always to mix up, to link the 2 experiences I had. So even today, I won't present myself as an aerosol scientist, neither as just an HVAC engineer. So pardon me if something is a bit in between the 2 approach, but that's exactly where I want to develop my talk with you. And this picture is like representing like a direct approach, experimental approach. We went actually in a hospital trying to measure the SARS-CoV-2 in the air. That was easy, not easy task. I have a good team of people that would just jump into any adventure with me. And actually here, like we are testing with the laser stuff and in the lab, some of the experiment we did with aerosol and try to solve something. I want to mention Dr. Vincenzo Gentile, Dr. Gianluca Serale, and my PhD student, Francesco Neirotti, who is about to defend his thesis, but also other collaborators at Polito, especially involved in the WHO collaboration, Dr. Marianna Nigra and Luca Galleano, and a big thank to Professor Paolo Tronville, who is leading real aerosol science in Politecnico di Torino. It's really vertical on this topic, so if you might be interested in aerosol science, I strongly invite you to contact him because he is not really making that much public, but he has great knowledge. Okay, so for today, I wanted to make a review of fundamentals. This is might sound trivial to some of you, but it's very important for my discussion. So we will discuss a bit about the air vector, its nature, and then I would like to share with you some engineering application I was involved in, and some also I wasn't, to come to some conclusion and orientation for the future after this experience. Okay, so when we talk about the vector for airborne disease, we're talking about aerosol. And we have been maybe a bit confused by news. We heard about droplet and aerosol, like they were different stuff. Actually, aerosol is a larger definition that includes also solids. So an aerosol is a volume of air where small particles that might be liquid or solid are actually included. So we are more interested in just the liquid in this case because the liquid comes from human activities and is where the virus and bacteria can be vectorized. So human actually, I don't know if I can move this or even hide this. Okay, we emit this aerosol of liquid. The liquid is mainly water. It's mucosoluble fluid. It's 99.5% water. But there are small amounts of the other molecules like proteins and some also inorganic and traces. And these are very important for the behavior, which is not exactly water, but for example, evaporation rate is very different. And we do emit while breathing. We do emit aerosol by talking, by coughing and sneezing as well. This is like more straightforward. And what type of particles, what is the range of particles we are emitting? Well, it's not easy to have a clear and perfect view of this because we are all different. But from a scientific, we have, okay, by the way, I would not say all the reference, but you see all the reference in the presentation, okay? So you can go after if you need to go deeper in it. But let me say that when we speak, the yellow one, we emit mainly in a range that is up to down to 10 micron and below. So between 1 and 10 microns. When we are coughing, we emit also larger particles in the range of 100. To have a comparison, our hair average diameter is 50 to 70 microns. So 10 microns is something that is not visible actually directly, but it's something that is there. And given that the virus is 0.12 micron, even a 1 micron particles can vectorize the virus. But not only we emit not all the particles will behave the same. Like if you take a particle in still air, and depending on the diameters, and you leave it, depending on the diameters, it will be falling down to the ground with a different velocity due to the balance between aerodynamic forces and gravity. So the smaller the particles, the more important is the aerodynamic force. And particles as small as 5 microns will take 20 minutes to float down from 1 meter high to the lower level, but 1 microns will take hours. Okay, so when do emit this aerosol, it's not going to fall down like a large droplet, but will stay around. And most of all, the air is never still in the room. We all know this. So the particles will be advected and will follow the air in the room. But not only they are behaving differently, they are also changing their size because of evaporation, which is clearly a function of the humidity in the room. But so when we do emit 5 microns particles, it might take like a few minutes to fall down, but in that time, it will evaporate to 1 microns or even less. Okay, so it won't reach the floor, but it will stay in the air and float in the air. It is the most similar like behavior we can think about when we talk about this is smoke. Even it's solid, but cigarette smoke will occupy the indoor environment. Similarly is the liquid aerosol we are emitting. Just a very larger particle, the one we sometimes notice when somebody is speaking or coughing under the light, will follow like a ballistic trajectory. So a more refined way of looking at this is to call it, well, the name also helps, we can call it a respiratory cloud, like Professor Buriba of MIT is doing in this very interesting paper. I have an aerospace background, by the way, so she's a fluid dynamicist, so I really like vibrating when I see, when I have this point of view. So like we are emitting turbulent jet, and the aerosol is entrapped in this turbulent jet. So at a certain distance from the mouth, you have, or maybe there was a pointer, it's no longer there, okay, that's okay. immediately the turbulent jet is also confined the particles, and due to, thank you. Okay, it's easier. Okay, so, but I have also to keep the mic on. Okay, so we have the very beginning 100% relative humidity. So that means that at the very beginning, the particles won't start evaporating. As they are, but it will be entrapped in this turbulent flow. And as any jet, there will be what is called a rate of entrainment, meaning some air from the indoor environment will be entrained into the jet. And having is like, you can identify the jet until a certain point where the rate of entrainment of air from the indoor environment is no longer identifiable with the background diffusion and dispersal. So at certain range, the background dispersal is of the same range of the rate of entrainment, and that is where, like, the jet is an area that we can identify as the end of the jet, is where what we emit is becoming dispersed in the indoor environment. This is very important to get following concept of today's discussion, and also to have a view of what system can be effective in the indoor environment, and the relationship between ventilation and distance, for example, mandates. So the smaller particles will be entrapped, and this is like a simulation of trajectories of these particles. The larger particle will just fall down. So this was the vector, but how much virus it is actually vectorizing? Well, it is very variable, and we understood from the very beginning of this epidemics that the viral load, so the number of virus that is in a infected person is very a function of the time of the evolution of the disease. Like in the very first 3-4 days, we have a peak, and up to 100,000 virus per minute can be emitted. RNA copies per minute can be emitted by an infected person in the very first day of the infection. And the virus won't last forever, but has been proved that at least 3 hours, and the orders of hours, it remains active in aerosol. So when we are talking about hours, we are talking about the usual rate of renewal of a room, which is normally we say it's 1 hour, 1 volume per hour, 2 volume per hour, or whatever. So it will remain active for a time that is the same order of what we normally do as a rate of renovation in an indoor environment. Then comes the subjective response, which is very variable, depends on a lot of aspect, and this is not my skills because it's medical stuff, okay? But there are models for this, and we can anyhow use it. So at a certain point, we have the vector we just described, and some viruses are on it. Then comes the contact. How comes the contact? Well, there are basically 2 possible scenarios. One scenario is that you are close to a meeting person, and you are immersed in the turbulent jet, in the respiratory cloud. After some time, the aerosol will be dispersed in the indoor environment, and after some times, all the indoor environment will share a background of concentration. So there will be 2 persons, B and C, exposed with the same dose. Okay? So now what we can do to control the background is clearly it's diluting it. So this is trivial, but sometimes it's also important to review and recall the specific concept. Like for ventilation, we talk ventilation, the substitution of indoor air with outdoor air, but also recirculation and air movements can play a role in this control of the airborne epidemic. So both of them are important, not to be confused, but both of them can play a role because we are talking about a 3D indoor environment, and it's not just a point. So if we if we adopt, as we always do, a simplified point of view, which is the lumped parameter, and we consider the room perfectly mixed, so the concentration is the same in all the room, we can write down the standard balance equation in a case where we have an emission, a source, and we have a ventilation in the room. The concentration will follow well-known laws. So just to recall them, we will have like an exponential law, and the concentration from 0, if we start from a clean room, will increase until a certain plateau. And this concentration equilibrium will depend on the ventilation flow rate. So if we increase 4 times the ventilation, we will have a lower plateau for the concentration. By the way, if the subjective, in fact, is just emitting and stay in the room for 15 minutes, after he leaves the room, the concentration will go down following this other exponential law. So it is quite standard for any indoor air quality activities to calculate the concentration, adopting a mixed ventilation, perfectly mixed ventilation indoor environment. But this is relevant also for infections. So the first thing is that modeling airborne diffusion is usually can be done also adopting some standard approach. So the aerosol actually is mixing, is moving in indoor environment like we consider it a gas. Just the dynamics is different, but in the end, we can apply the same rule. So now comes the subjective response. As for the subjective response, has been done a lot of work in the past, and like seminal works by Wells in the 1950s, and Riley's in US. They would be working with tuberculosis, and but then this model had been applied to other diseases like measles and influenza, etc. And basically, they find out experimentally like a relation between the time of exposition to the bacteria, in that case, related to the ventilation flow rate. So this standard equation from those time has been evolved in more recently, like in the 90s, but the basic concept is still the same. Like the probability of infections that we define as the ratio of cases to the susceptible, is a function, exponential, is following this exponential function, where the higher is the emission, where that is identified in the equation by I, the number of infected person, and Q, that is the the quanta emission, and I'm gonna talk a bit about this, and the ventilation, the respiratory flow rate for each person. So this IQP is identified representing the emission, the source, and the ratio of this to ventilation flow rate. So in the end, if we are in a room, like this is an example, 100 cubic meter room, there is one infected person that is breathing and talking, like office activity, with no mask, and we adopt the estimation of quanta that Buonanno did in this paper, Buonanno and other in the group. We can draw up a similar scenario, like with the 1 volume per hour. After 1 hour in a room with an infected person, you are exposed to up 60% of probability of getting infected. But if you increase ventilation by a factor of 6, you can reduce it to like 15%. Okay, all the figures we will see about probability are subjected to high uncertainty. So don't get this 60% as like, wow, is this so solid? It's might be 40, 70, depends on a lot of subjective reaction. But the concept is that if we increase ventilation, we can reduce this risk, but we must increase a lot. It's not just that we increase by 20% or 30%. We must increase a lot of ventilation in order to reduce this. Well, I was saying that quanta is the viral load that is able that is, if uptaken by a person, has a 63% probability of getting this susceptible person infected. It's quite a complicated concept, but you might consider it the minimum amount of virus that would get you infected, almost this, okay? So basically, they would derive how many quanta per minute a person would emit under different conditions, different activities, like breathing and talking. Okay, so this clearly has to do with energy to us in the building sectors. But it's kind of crazy evolution because nobody wants to stay in a room, in an office, and exposed to 60% of the risk. So we want to get it down. So if the first reaction might be, let's zero this risk. Let's make us in a situation with zero risk. Let's think about it. Well, zero risk does not exist, we all know. But if we consider like this example, an office of 200 meters square, and let's say 40 people are working, like in an open space, and out of them, 10% are infective. Well, it's not very common that all of them are infected with at the same moment of the evolution of the infection. But if we stay 4 hours there, the probability of infection can be calculated by this Wells and Riley equation I showed you before. But if you apply standards Ashray condition, it will come to roughly 8.5 liters per second as an average per person, outdoor air. That will count up around 2 volume per hour, air change per hour, which is kind of standard. And under this condition, the infection risk after 4 hours is up to 41%. So it's very high, okay? Well, it's not so crazy because if I think about influenza, and it is almost the same risk, very similar. And it's quite common that if you spend time with somebody in a room and he's got influenza, after one day you got as well. So the figures are, as I was saying, are not sharp. So consider, I'm not inserting any uncertainties because even calculating the uncertainty assessment is very hard to be done because there is subjective response in behind. But anyhow, let's take it like as a range. It's very high anyhow. So if we want to increase it like to a factor 3, in that case, the risk is reduced to 60%. But let's say we wanted the risk less than 10%. We go up to 12 volume per hour, which is actually a clean room. And it's 51 liters per second, and the risk is still 8%. I'm talking about spending 4 hours continuously in a room. It's a very high risk. So we are increasing the ventilation by a factor 6 or a factor 12. And this clearly comes with a huge energy cost. Like, for example, in New York City, you have also heating, and you're increasing a lot the power. This is, well, just power in an average condition, not even the design condition. So you can imagine energy comes after if you define the profile, etc. But just to have an idea on a certain condition, you will increase by a factor of 4 the heating and the cooling. Especially the cooling in the area of the world is a big issue, okay? Like Beirut or Singapore. Singapore is the worst for this. So it's a lot of energy, of more energy that is needed. So that's where it comes the be safe, or we are going to save. We have been oriented to save energy, and we want we want this transition, we want to reduce CO2 emission, but now comes the pandemic and it say to us, no, you don't have to save. You have to be safe, increase the ventilation. And suddenly we are really at a crisis moment because we have to decide what to do. We're going to stay the same and risk ourselves in the future pandemics. We're going to consume more energy as a base load, we're going to adapt our buildings to have a dynamic response to pandemics. Well, clearly it's the third, but it is not most likely it's not possible to choose the second because it's too much energy needed. Well, again, what I was showing also after, and the probability of contagion we are going to see again, please don't consider them as sharp figures, okay? Because there are a lot of assumption behind. The main assumption for this type of calculation is that you have perfectly mixed ventilation. So the concentration in the room is homogeneous everywhere, which doesn't come so frequently. And this can be like a danger to us, like meaning the ventilation is not effective, so we have actual higher probability of contagion than the calculated one. Or it can come also as an helping factor, because we might have in the room better condition than the average. So this must be considered. Okay, today I would skip all other models that have been derived, but let me just cite the Maitoni-Nucci, who is kind of a development of the Wells-Riley approach and is giving more flexibility with especially with reference to the concentration at time zero in the room. Okay, so this is what I wanted to review with you, like basic concept, and now I want to share some observations that comes. I will start with something that is not mine, and this is supporting the asymmetry of flow topology in a room. So it's the mixing, perfectly mixing approach in the modeling is far from reality, but like in this example was so far that is like striking, okay? And this came at the very beginning of the pandemics, and at some point also the news was like spreading like the air conditioning system are dangerous. So don't turn on the air conditioners because it's dangerous. It's increasing the diffusion of the contagion. And mainly this comes from experience like this one. Well, there was this restaurant in China, and it is being later very well analyzed by Hugo Lee, Professor Hugo Lee of Hong Kong and the colleagues. And basically what happened was that there was a person, this purple person here in the middle table, that was infected, and all the red one got infected. So by those time, even WHO was saying it's not airborne. Like the COVID, the COVID is not airborne. If you stay 2 meters or whatever it was, you are safe. Okay, it's just large droplets. So what is important is that you don't touch surfaces where some droplets can fall and can diffuse the virus. But actually, it was like a striking experience where it was airborne. There wasn't any other possible explanation to this. Okay, so the thing is that the system, the air conditioning system, was based on huge gradient, and this flow topology with this like vortex, big vortex, because the fan coil unit was hanging on the wall, and like any recirculation unit, there was like doing similar and imposing this similar vortex, large vortex shedding into indoor environments. So some aerosol emitted by the purple infected person have been transported to the forest table, but also the flow back has been involved in transporting and diffusing the aerosol in this particular bubble and not in the rest of the room. Well, in the end, also, the ventilation flow rate has been stated is very low in this indoor environment. So first of all, a huge contagion happened because ventilation was very scarce. There was a couple of a small grill where in a very huge room. But this bubble, this recirculation bubble, help spreading to near tables the contagion. You see, there is always a good in the evil, and the evil part is that 2 tables has been involved, but the rest has been like preserved. So this recirculation in some way also confined the situation. Well, it was interestingly enough, it has been also tested with AI technology on the video that no contact has happened between them. So this was like a proof that the airborne stuff was really solid. Okay, so let me jump to an experience of mine. I would be very summary level. Let me say to large view of the topic. So one of my activities, I'm also reviewing projects from UN nation projects, yes, programs. So one case I received a new hospital designed to review, and it was in Guatemala. And many of this review was based on money transfer coming from World Bank or whatever to help COVID response in all these nations. So it was very important that all the standards and recommendation about COVID were followed. You might know that WHO is published guidelines for this. Especially recently, there is one that's called SARI, Severe Acute Respiratory Infection Disease Guidelines, that I'm also involved in the revision of this, the reviewing of this. There will be review number 2 out in some months. But the basic guideline was for acute, in intensive care units, you must follow 160, you must provide 160 liters per second. So remember the standard is 80 liters per second, 160 liters per second is the guideline, okay? But even in this mechanical ventilation new design, the design was not providing this, and actually it was providing a bit less, like the half. 6, that corresponded to 6 volume per hour. So 6 volume per hour is considered, also by ASHRAE, is the lower level of the range, 6 to 12 volume per hour, that is considered good design for intensive care unit. So from some point of view, the design wasn't bad. It's quite in the standard. But talking about COVID, we had this guidelines 160. So what we're going to do? So we had this discussion with the project team. But in the end, they would say, okay, come on, we are in Guatemala. If we are going to increase the rate of ventilation in a hospital where we don't have that much heat recovery, we cannot. With the humidity we have in Guatemala, we got to spend a lot of money. And most likely, we won't use those systems because of the energy costs. And actually, this is kind of like it might be resolved by me by saying, okay, this is the standards, you apply the standard, and that's all. But actually, the question is a very good question, what we're going to do. And so just making a simple calculation, the probability for healthcare personnel staying in a room with a severe patient half an hour in the 2 scenarios with the WHO guidelines and with the current design. The current design, the probability of infection was in the range of 9%. With the WHO design will be 5%. I'm talking without mask. So if they have personal protection equipment, this risk can be even reduced. So it's 9% too much or 5% enough. It's like we are missing something. We cannot say like usually we do, it's done. It's always a matter of a smooth border between situations. Anyhow, moving from 9% to 5% of probability in half an hour staying in with the infected would add cost for 80% to the consumption of the hospital. So maybe the designer were right. In front of real, it's better to have like a reduced risk approach instead of going for the best you can think about in the world, just because in the real world you won't spend those money because you don't have them maybe simply like that, okay? So it was kind of a very instructive stuff. But just the picture is not saying nothing, just that it was a very well-designed hospital. So we are not talking about a low-level activity. So on a totally different ground, we were also with WHO, we were designing in very low energy scenario. Like Burkina Faso in this case, and the mandate for the project team was, we cannot make it a mechanical ventilation building because we won't have money for the maintenance, we won't have money for paying the bill, okay? So this could have been done just with natural ventilation, hybrid ventilation, okay? So we designed some natural ventilation, and it is intensive care unit as well. So you need to have the cell, the patient's room, to be insulated. And the basic goal for you when you're designing is not to preserve the people inside the patient because they are already infected, but to preserve the healthcare. So people, the healthcare should not be infected and should not spread all through the hospital the infection. So we designed like two independent volumes. The corridors would be kept at reduced pressure, negative pressure compared to the room, by means of exhaust extraction. So there will be some fan into the cells. So the corridors and the restroom. The restroom will be put in negative pressure by fan, so we are sure that there will be negative pressure there. And when people are moving into the room and into the patient room, there will be this like intermediate area, and this will stay negative pressure. And there we added some inlet into the project from at the bottom of the corridors, okay? So this is basically where healthcare will stay, and they would enter a room. But the room is totally independent, and the natural ventilation of the room will get airflow in from the windows and flow out into this area. So we made a double roof system, so each room can be independent in its ventilation, in its natural ventilation, and the corridor will form a safe area for the healthcare. This is clearly based more on the wind-driven ventilation. And when you do natural ventilation, you cannot just make a design point. You have to go and calculate what is happening depending on the wind behavior. So you need a set of weather data that you can trust, and you make early calculation. And so in the end, you come to a statistical analysis and you say, how many hours per year or per week I can provide the minimum ventilation that is needed for safety. And this is one point. So the tools are totally different from mechanical ventilation, and the approach should be a statistical one. Like how many hours you are having more than 160 liters per second, and then you have an additional difficult choice. So how many hours is the limit to consider validated the project? Again and again, you see that there are no sharp rules. We need to exercise a bit of new approach in this ventilation that is not just you follow a simple rule, but you need a smoother approach on it. Okay, by the way, in Burkina Faso, you can make natural ventilation effective, as we did. Okay, let me just tell you one thing. We're relying on windows, how cultural factor can affect. We're relying on simulation on windows opening, but actually people there would say to us, nobody would keep the windows open during night. Oh, why? Well, because we are in a wild area. Okay, so the animals. No, it wasn't about the animal, because in their culture, at night, you cannot open because of the night spirits. And some people would close the windows because they would think that the night spirits could come in. Okay? So it's, can make us smile somewhere. But if you're making, another lesson is if you're making the design and you're just thinking that the people would act as you think, but maybe it's better if you check, because it's better if you understand what is the cultural background at all. Okay, natural ventilation is almost zero energy in this scenario. Another scenario simply cannot be applied because like in Torino in winter, you go for natural ventilation, people will freeze and will close the window. And during summer, they would just really sweating all the time. But even in that scenario, which is kind of moderate, and the people are more used to extreme condition, it was very important to apply this also to make a good design for comfort. So we added this double roofing for ventilated double roofing in order to assure a lower radiative temperature inside the room. Okay, jumping from Africa to Italy, okay? So other important buildings. Well, the hospital are really central to all the epidemics because people would start going there and the healthcare workers, if not correctly protected, can spread the contagion, and from the hospital, it can spread, instead of being contained, can even spread to a region. So hospitals are really the prime concern. But then comes working area, like office. Like in this case, a bank asked me to assess their strategy in all the branches and in some offices area. Like they have 3 huge offices building like this one with a open area, big open space. And like, I don't know here how many, 70 or 86 seats per area. So it's quite a complicated situation. And they would just be able to increase ventilation, and they would ask not to keep too many people at home because they purposely make the open office because they don't trust maybe their employees. They want them to be more controlled. And so it's totally opposite to let them stay at home. They wanted to have a number of people inside. So we try to conceive a strategy for them. So one point is increase ventilation. The other possibility is to make a strategy. And so we were thinking about, okay, the more time you spend with an infective, the higher are the probability. But what happens if you just stay small time with it? Like you stay 1 hour, then you go out. And then and you let the air reduce the concentration into the room. Then you come back, and you have again an exposure, but the exposure is not continuous. So this is like a bit of shortcoming of the tools we got. So we used some current tools, but the probability, I think, is not really you cannot trust really this probability, but you can trust the concentration. So people would jump in, let's follow the blue one, which is the current scenario, would stay in the room, then after few hours would have a break of some 20 minutes, 30 minutes, and the room would be cleaned down, then would come back, then there is the lunch break, and the room would be cleaned down by ventilation, etc. So this is the basic scenario, and we calculated this with how many people are there, and what the share of infective. That depends on the current pandemic's condition. So it is possible in this case, if you don't have the opportunity to increase the ventilation, to include some local machine, local device. Like we started this the application of portable units that comes with a HEPA filter. So basically, the filtered air is clean air as it is outdoor air, basically. So adding this portable unit to the volume with a good distribution would have the same effect of adding outdoor air. So we planned this like adding 8 units or 16 units in all these big spaces, and then we calculated the reduction. Okay. So this case, the strategy was approved, but we could not monitor what happened in terms of contagion inside the building. But I think that the strategy can work for a bank. Like you have some portable machine, you can add if needed. You just you just read the news. What is the current situation around? What is the share of people infected? And following on that, you apply a management strategy of people. So you say, okay, 50% of the people must come to work, and 50% stay at home, and the people at work would need a break. So you need just to organize places where they can have a break, and all these places must be safe places, like it's better if they are terraces or whatever, and then they take a break. Well, in another work, we had this museum association, Foundation of Museum in Torino, and they have 3 museums, and they asked us what we're gonna do during the pandemic. So should we close? Can we be open or whatever? And this is, I think, this is interesting as a general outcome. Well, the situation was, this is Galleria d'Arte Moderna, modern art gallery in Torino, and as you can see, there are huge halls, but there are also paths that you can walk by into small rooms, and in this case, you have like a larger room and 2 smaller room, and you usually follow this. Okay, so what is the risk assessment in this case? Well, you must make scenarios, because people won't just stay like in an office, sit in there. There might be an infected person, and the infected person might be walking with me all through the visit, or it can be, it can stay 30 minutes in a room, then leave, and I go into the room after he left, and I got exposed to his infection. So we imagine some scenario, and basic scenario, I think the most dramatic would be you are going around with somebody infective, and the infected person is walking with you. Okay, one of the questions that all the people that ask us consultants, like museum, office, and the airport as well, etc., was they were concerned, especially the building where they have full air service. They were really concerned about recirculation, because there was a mandate to switch off recirculation, and that means a lot of energy again, a lot of energy that you must spend, and in some cases also that means that the system wasn't able to meet the load. But if you think about this case, the recirculation is not necessarily might be seen as a bad factor. Could have been even of some help. Why? Because think about this. When you have an infected person in one of the 3 rooms and you have just outdoor air, well, what happened is that clearly the 2 other rooms are not involved in the dispersion of the aerosol, infected aerosol, okay? So this what the regulatory guy were aiming for, okay? But if you add recirculation and you have the same one infected person in one room, the recirculation, the green path, will spread the same viral load into also the other 2 rooms, which is bad because the 2 rooms were safe. But on the other hand, the spreading the same source, the same amount on a larger volume means that you have a lower concentration. So one, at this point, must think about, okay, it is better to be exposed to a lower concentration or to a higher concentration for a lower time. Yeah? And if we apply this standard simulation tools, we find out that actually it's worse to follow a path with an infected person in the 3 room, in case you have full outdoor air, then in case you have also recirculation. Like the probability, it's just minutes, so the probability is low, but clearly the orange one is with recirculation, without recirculation. You stay in this room, the concentration is increasing, you're going to the 2nd room and again and again and again. While if you follow the same path with the recirculation, it's like like you are in a larger volume. Larger the volume with the same quantity means lower the concentration. Lower the concentration means lower risk. So even this simple rule, like you don't do recirculation, is not that straightforward. We should think a bit about it. We might not have the tools exactly estimate the probability variation, but this is some food for thoughts. Okay, I'm a bit late, yeah? I'm asking, how many minutes are you? 10? 5 minutes, oh my gosh. Okay, so this was actually one of the most interesting parts of the presentation. I'm gonna do it very quickly. So, everything we said about this until now is about background and the concentration. But actually, there has been a lot of effort about the short distance because we all had like stay 2 meters away mandate. Professor Hugo Lee and colleagues introduced this interesting diagrams where they consider the background in the blue line as a function of time. So this is exactly what we saw before. Like the concentration, you have a source in a room, the concentration will increase in time. And then they consider a diagram of exposure of at short distance as a function of distance from the source. Like you are here, and you have different exposure as you are moving far. Okay, so the concentration at short distance is very high, and it is reducing. At some point, at some time, the exposure you have at short distance is the same that you have on the background. So there, for a certain time, like time 2, the exposure of the background will be this one, and there will be a distance at which you get the same exposure that you have in the background. Okay? So this interesting concept to discuss the interplay between short distance and long distance. There might be a lot of things to say about it, but let me just take this diagram to think about in this way. We have ventilation, okay, we increase ventilation, we have reduction of exposure, but at short distance, what we're gonna do? We can increase even ventilation, increase, because also at the lower distance, there will be lower ventilation, but clearly, there is this need to do something at short distance. Otherwise, we're gonna spend so much money for the energy. And the options are clearly already in many parts already explored, like ventilation at local level, the personalized ventilation, the possibility of local filtration with portable units, even wearable filtration units. But there is also the possibility, I think this is a bit under explored, of just controlling the flow with simple design of topology. So as for personalized ventilation, well, also here in AUB, you made a lot of work. And so there is a lot of very interesting stuff. But, and the basic assumption, like Professor Melikov team was stating here, is like with the same flow rate, you can get a very low reproductive number for an infection disease. And even you can get with the original 10 liters per second, you can get less than you got with 40 liters per second with mixed ventilation. So the efficiency of the ventilation is very, very important, and you can reduce energy consumption by this. Nonetheless, you need all this ducting around. So even for an existing building, it's not straightforward. They can install new ducting for the local ventilation. For new building, maybe it's easier. But as a matter of fact, in the last, it's like 20 years at the least, this is from, well, this is most recent, but Melikov studied this back in the late 90s, most likely. On an industrial level, is not that much is happening. It's like, or the system, either the system are not understood, or economically speaking, they are not very well developed, but they are not still there that much. We need more stuff. Well, the industry is also developing portable filtration unit. Like big names of industry are presenting this like portable devices with filtration unit. And there is a last way we can try to do is local control. So the basic idea is I go here and reduce this. But for the rest, I still need dilution. And we try this way at my lab at Polito with very simple device. The basic idea is we try to get a good, effective devices with very, very cheap, very simple devices. And actually, it's just like a small devices you put on the table, and it's generating 4 air blades. And the basic concept is that the infected person is in front of a V blades, and the induction that is generated by the V blades would curb the respiratory clouds. Then you need dilution, but at least at the short range, you don't have the direct contact. So we tried this, and we had a setup with our friend Joe here, the mannequin, with aerosol. And clearly, if you want to make it really realistic, you would go in a clean room. We didn't have budget for a clean room, and so we increased the density of the aerosol. So these are not real figures. So it's like 10 times the number of particles emitted in order to be able to identify them compared to the background particles that was there. And we just imagine sitting at a table, and the device is in the middle, and on the other side we have a probe with an optical particle tracker, the classical TSI 33. You are also using that one. I saw you in the lab. Okay, so the basic idea was let's compare. Okay, so we visualized the aerosol with the fluorescent and UVA technology, and when you are talking, breathing, and the aerosol is flowing on the other side to the other host. When you are turning on the V blades, the respiratory clouds in some way trapped in your area. Okay, and under the particle you are reading on the side at this probe, we had like a reduction in the range of 60 to 80%. Okay, it's clearly is not the silver bullet, but actually it's better than the mask that you cannot wear when you are eating. And the devices costed like to us costed like $30, and if you produce it in series, might be, I don't know, $30 might be the final cost. So you can take it, you put it on the table, it's doing something at the local level while you are sitting around. You can even bring with you. It's a perfect Christmas gift with the logo of AUB. Okay, so okay, so just to conclude, and well, I didn't show much statistics, but we all know the buildings where we are consuming a lot of the energy and are almost 1/3 share of the emitting CO2, and clearly indoor environment is where the contagion is spreading, okay? And the fundamental knowledge about how it is spreading is available. So we had incredibly crap news about, well, like the news wasn't able to get the concept, but even worse, even at a higher level like at WHO, and they are now admitting it, they diffuse, they spread wrong news, like it's not airborne, you must clean everything, while the most important thing was to ventilate. And so we know it is not necessary that we get this. And after this, if we go for a zero risk, we would be destroyed. It's not possible. How can we just face 5 times increase of energy costs? It's not possible. So we must go for a reduced risk, mitigation risk, that is clearly dynamic, and you can adapt to the current situation of the pandemics. And to me, this should include an increased ventilation flow rate as an average, but there are also other options. You like portable filtration, or also the filtration as on a centralized system is very important, can be like effective as ventilation. And near field control devices are, to me, are some hopes, okay? Very simple control device for the topology flow. Okay, and I'm done a bit late, but by the way, this is our mannequin with a mask. You see that the standard mannequin mask is not really well sealed. Anyhow, it's spreading something.
Thank you, Dr. Marco, for this interesting, enlightening lecture about the risk of contamination and the ventilation rate. We can have few questions from the audience. Jennifer?
Hello, doctor. Thank you for your presentation. It was so interesting. I have a question about the portable air cleaners you put in the office. Okay, so the operation of these air cleaners is dependent also on the airflow rate of these cleaners, the position of these air cleaners, and the direction of supply. So how did you choose those parameters when assessing your model?
Yeah, well, actually, it's like a balance between a trade-off between economics and a good homogeneous diffusion into the environment. So actually, we did some CFD 3D simulation, but we never came to the perfect solution with the client. So in the end, we just try to say to them, you put it not everything in the same place, but each table you put one, and consider that the jet, you should not direct directly in face of the people, but let's try to use it mixing the air into the environment. So basically we consider it like additional outdoor air. So we needed like 5,000 cubic meters per hour more, and we had like 100 meters a room. We tried to say, okay, let's apply 10 unit or 400 cubic meters per hour if it's possible. So it was a kind of empirical, actually. It's better than nothing.
So you did not consider like filtering the air in places where the occupants are not present, let's say in the unoccupied room and the upper zone, using lamps, UV lamps, UVGI?
No. Well, actually, we talk about UV lamps, but this was a real case. We had big constraints. So the client wanted, it was really even hard to let them buy this the portable device. So clearly, the UV lamps in the top has a good efficiency, has been proved. So it's an option. But they wouldn't accept it there that much because they would say, okay, it's an over the occupied zone. But what if some of us stupid guys take a later because they want to remove something and get into the zone? We will have great issue with our employers. So sometimes things that you must consider very clever simply in the real world are not acceptable for different reasons.
Thank you so much.
My pleasure.
Danny?
Thank you for the presentation. So I have two questions regarding the simulation models. Did you use deterministic or probabilistic simulation models?
Well, actually, the simulation per se is deterministic because it's giving a figure, but the number is a probability. So what is behind, it's like a probability. But they, they derive it experimentally. Like the original experiment was like this. There was like a room with infected TBC person, and in another room that they put in contact just with air, they put Guinea pigs. And they moved the aerosol, infected aerosol from the patient's room to this cage with Guinea pigs, and they counted how many Guinea pigs got infected as a function of time and as a function of the flow rate. And so you got a correlation, and so you use the correlation. So mathematically speaking, it's deterministic in the sense that you just put one input and you got an output. So there is not a set of distribution, there's no assessment of uncertainty. You can just use it as it is. Input is one figure and some factors with one numbers and output. You can also use it with a larger span of numbers. You want to make a sensitivity analysis, okay. But in the end, the probability is just one number and that you got.
Thank you. And what about uncertainty quantification? I think, so did you do any uncertainty quantification?
Well, I couldn't do nothing on this kind of model because it comes from it's on the medical side of the story. Like the subjective response to the infection is really something that I cannot make that much with my tools on. So I can make uncertainty analysis on the distribution of air in the indoor environment, but then I don't have anything to do this with the medical part of the story. So,
Thank you, Dr. Marco. Okay, If you have any questions, probably Dr. Marco will have the questions outside.
Excellent presentation. Thanks so much.
The final question.
Okay.
Final question.
I'm very happy to see that scientists start to speak the language of designer, and something very important. I think what's missing, in my view, from the whole analysis, is to really work on the filters. And ASHRAE, you know, I was on the epidemic task force of ASHRAE. When they kept the ventilation rates as per described standards, they really upgrade the MERV to 13. So I believe that you know, location of the diffuser and the filter performance are very important keys, given the ventilation is so costly.
Yeah, I see it the same way. I just mentioned cell-only filtration, but anyhow, if you have increased, it will be important from the energy point of view, but will need anyhow to install more and more stuff in. So if it's portable units, easy. If you need to increase the circulation of filtered air, anyhow, you're spending money for, you have new capex and you need larger size ducting, et cetera, et cetera. So I have the same feeling that filtration would play a very important role, but you cannot increase by factor 6 the current ventilation, even with filtered air in a room so easily. So I think we should find a trade-off. Clearly, I'm on the same page.
Thank you, Dr. Gaddar. Yeah.
We'd like to thank Dr. Marco Simonetti for this interesting, very interesting and relevant keynote. And as a token of appreciation from ASHRAE chapter at Beirut, we'd like to give you this trophy so that you remember us with.
Yeah,
So
sure.
we're gonna go here for.
Very much. Thank you very much for inviting me.